Hi, welcome to my channel. Today I'm going to talk about transformation. These videos are clear with examples and graphs, and I'm doing my best for this video and the coming one, which is related to it so much, not to go over 20 to 30 minutes. So let me do my best and we'll see how it's going to go. We're going to talk about identifying horizontal shifts, identifying vertical shifts, and see it from graphs. Here we go. So vertical shift. In vertical shift, given a function f of x and new function g of x equals f of x plus k, adding a constant k outside, all the way outside, where k is a constant, is a vertical shift of the function f of x. All the output values change by k units. If k is positive, the graph will shift up, and if k is negative, the graph will shift down. So by adding this constant after your outputs that used to be called f of x, now you have new outputs. The original function was y equals f of x. Now we're adding k to our outputs f of x. Let's take a look at the graph. So as a graph, if this is called f of x, and we're adding 1 outside it in a value, this point will go up 1 unit, this point will go up 1 unit, every point will go up 1 unit. So as you could see, the new graph in red is the same graph shifted up 1 unit. That's called vertical shift, by shifting it 1 unit up. So this is a vertical shift by k equals 1 of the cube root function, the cubic root of x. Here's a graph. Doesn't have to be smooth like cubic root. Adding 20 to each of the output values of the original function, we'll have the following. Taking your time, you could see it from the table that this is v of t, and the new function in red, it's called s of t, will be 20 units being added to every single output of v of t. For example, at the origin we have 0, 0. So 0 for t, v of t is 0. Now s of t will be 20. Because you are here, you're adding 20. You go up to 20. 0 will be 20, 220 will be 240, 220 will be 240, and so on. If this is 220 originally, I should go up to 240. Everything gets shifted. The best way to do it is, if it's a graph, take the major points, the corner points, and the rest will follow. Identifying horizontal shifts. Given a function f, a new function g of x equals f of x minus h, where h is a constant, is a horizontal shift. So when you are adding or subtracting from x inside, not outside, what we used to call it k in the previous slides, that's called horizontal shift. If you're adding outside a k constant, that's called vertical shift. You're affecting the old y values, but inside you are actually affecting the x values, and that kind of helps which one is which. So if you're adding to x or subtracting from x inside, you are going right and left. If you're adding a constant k outside, you're actually going up or down. So this one here is kind of like a formal way to say it. If h is positive, the graph will shift right. Well, this one right here, it's x plus 1, but when I compare it to this one, it's actually x subtract negative 1. So if h is negative, in this case, h is negative 1, it's x minus negative 1. So h is negative 1. You shift the graph to the left 1 unit. It's kind of hard to see that this got shifted, because if they stop the arrow here, you'll see that the red one is being to the left. The best way to look at it is a major point like this one. I could see that it's 1 point to the left. And this should be like also maybe extended to show you that it got shifted to the left. So sometimes students say like, so if I add 1, I go left, and if I subtract 1, I go right. I say you could say that. You could do it a lot of different ways. You could plug in the points and test it. But here we go. I'll do that maybe in different examples, not with the cubic root. Now, notice that the graph is identical to the shape of f of x equals x to the second. I could see x to the second starts here and goes through 1, 1. Look, it's kind of like 1, 1 idea. But it got shifted to the right 2 units. All right? When you subtract 2, that's an h 2, x minus h. You move it to the right 2. So that's a new function. It's x minus 2 to the second, where I'm subtracting 2 from x, and it's a second degree quadratic function. Now sometimes to support that, why we are here, not on the left, I tell my students just plug in 2 to test that this is the vertex, which is 2, 0. Yeah, if you plug in 2 here, 2 minus 2 is 0. 0 to the second is 0. So yes, this belongs to me or to the graph, or this equation agrees with this graph. You could also plug in 3 and get 1. Look, 3 minus 2 is 1. Square is 1. So when you subtract 2, x minus 2, you go right 2. Formally, it's called x minus positive 2, and 2 is h, which is positive, you go right 2. Now this is a absolute value function. To do the following, f of x is a absolute value, already graphed. A new function from the basic or the parent function, doing the following. We know this is a shift up or down. In this case, it's down 3 units. Plus 1 will take you back to the left 1 unit. So this is what's going to happen. Let us follow one point of the graph of f of x, which is absolute value of x. The best point is 0, 0. The point 0, 0 is transformed first by shifting left 1 unit. So if you're adding 1 inside, you're going to affect it by going left 1 unit. So you will be here at -1, 0. The point -1, 0 is transformed next by shifting down 3 units. -1, 0 becomes -1, -3. Instead of saying all that, through the grid it's easier to see it. And here's what the grid says. I have the original graph in blue. First I'm gonna take it left, take the whole thing, but kind of like holding the mouse at this point and holding and clicking on the graph and drag it to the left. That's shifting it to the left 1 unit. Then drag the whole thing, the red one, dashed red, down right here, 3 units down. And the final graph will be the green one. That should do it. To graph it without all these steps, here's a new function. It's an absolute value with the same angle. The angle is 1, 1. And as you can see, 1, 1. It doesn't change. It doesn't open wider or narrower. And we're moving it from here to the left 1 and down 3. So the vertex will be this location instead of this location. Reflections. Given a function f of x, a new function g of x equals minus f of x. If the minus is outside, it's a vertical reflection. Why vertical reflection? Because if you have a 5 up here, -5 will go down here. Sometimes called a reflection about or over or through the x-axis. What's a horizontal reflection? So if you are to the right, you become to the left, and if you are to the left, you become to the right. This is when you affect the x. So instead of being at 7, now you are at -7 because you are affecting the x. And going this way, horizontal reflection, it's kind of like reflection about the y-axis. That's what we call it. Notice the original graph in blue, which is f of x. If you want to go horizontal reflection or reflection about the y-axis, it is now graphed this way. Instead of going right, you're going to go left. And instead of going down, you're going to go down the other way. If you want to go this way, that's called vertical reflection. You're going to look at x-axis as the line of reflection. So going away from the line of reflection, you're going to go away from the line of reflection the other way. So that's f of x, that's negative f of x. Negative out, that means my y values are now the opposite. And for between this one and this one, it's instead of x, you're saying opposites of x. So that's a reflection about the y-axis or horizontally. A vertical reflection this way, that's from being up going down about the x-axis, you'll have the graph down this way. This is vertical reflection of the square root function. So a minus outside, instead of having positive values as an output, you're going to have negative values as an output. This would be called square root, and this would be called negative square root. This is a horizontal reflection. So instead of going this way, reflecting about this line, you're going to go horizontally, reflect, and you're going to be on the left, as you can see. So whenever you replace t with minus t or x with minus x, you are reflecting about the y-axis. Here's 2 to the power t. And we're gonna sketch the new function k of t, which is minus 2 to the power negative t plus 1. We're gonna take it step by step. I have 3 things being affected or applied. The minus, the negative sign next to t, next to the input, the minus sign up front, and the plus 1 outside. So here's how it's gonna go. This equation combines 3 transformations into the equation. A horizontal reflection, because t was replaced with minus t. T was replaced with minus t. First, we applied the horizontal reflection. So instead of, we're going to reflect about the y-axis. So instead of going this way, we're going to go the other way. Going this way, that's going to be reflected here, and this piece will be reflected down here. All right? So that's a reflection when you place t with minus t. Then the minus outside, so we took care of this negative, now we're going to take care of this minus outside. That's going to be a reflection about the x-axis. It's called a vertical reflection. So reflect this about the x-axis. I get the following. Now we're going to add 1. And we're going to shift the graph vertically up 1 unit. You could trace it and look at these points and see like how you're going to take this point up and take some other points up one by one. And that's the new graph. The major point that I could see right here is this point, which is originally, or I don't have to trace it all the way with the original points, but this point is 0, -1. By moving it up 1 unit and moving all the other points up 1 unit, you're gonna go through 0, 0. I think that should do it for this one. Step by step, you work from inside out like order operations. You apply this first, then you apply this next, then finally you apply this. Let's talk about even and odd functions, which was mentioned in the previous video, but here in more detail. An even function, if for every input x we have f of x equals f of negative x. In other words, f of x and f of negative x are the same. For odd functions, f of x and f of negative x, they are opposites. Alright, that's the main difference. You see the minus sign here, it's not shown here. This right here, going right and left like 5 and negative 5, you get the same output. That's called symmetric about the y-axis. This right here is, in short, called symmetric about the origin. We're going to see some examples and some graphs. This is an even function. Comes from x to the second, y equals x to the second. Notice at f of 2 we have 4, and f of negative 2 equals 4. So that's kind of like x, and that's like minus x. F of x and f of minus x are the same outputs. That's called even. A good way to remember what's even is related to x to the second as an even exponent, the basic one, not any x to the second. Because if there's shifts right here, right and left, it doesn't apply. Just compare to the parent function y equals x to the second. F of negative x equals f of x are the same. F of 2 and f of negative 2 are the same. They're both 4 as an example. Odd functions. The best example is the parent function x cubed. And that's another way to call it odd because of the cube. Horizontal and vertical shifts produces the original cubic function. Take a look. X is being replaced with minus x. So we're going to reflect about the y-axis. Instead of being right, we're going to be left. That's called horizontal reflection. So what's on right, now it's on my left. What's on right, now it's on my left. What's on my left of the y-axis is now on the right. Now to do it now vertical, a reflection about the x-axis, this portion on top will be down, as you can see. This portion down will be on top, but you get back the first one. That happens in odd functions. So odd functions, they have two reflections about x and y, or differently called about the origin. What do I mean by about the origin? You see this one here? That's 1, 1, right? You see this one right here? That's negative 1, negative 1. It goes through the origin to get to the other side, or the other point. We have 2 will take me to 8. I don't see the 8 here. But 2 takes me to 8, and negative 2 takes me to negative 8. So if you connect 2, 8, and negative 2, negative 8, you could see it's on the other side of the origin. As like the point as the origin is being the point of reflection. Alright, so anyway you move away from it, you will be on the other side from first quadrant to third quadrant. That's called reflection about the origin, and symmetry about vertical and horizontal reflections about x and y axis. Determine whether a function is even or odd, or neither. One way to graph it is, if it's symmetric about the y-axis, we call it even. If it's symmetric about the origin, we call it odd. But sometimes, maybe we don't have the tools to graph it, we could do it in a different way. I have x cubed plus 2x. If f of x is the same as f of minus x, we call it even. If f of x equals negative f of negative x, or the opposite of f of negative x, we call it odd. Here's our function. F of negative x. We want to see what's going to happen. So just stay with me and you'll see exactly what I'm taking you to, and trying to make it clear with those boxes and summary. So if you take minus x and plug it in right here, what happens? Negative x to the third 2 times negative x. Negative x times negative x times negative x will be just negative. An odd number of negatives will stay negative. 2 times negative x is minus 2x. Let's try this. Well, this is the opposite of f of negative x. This is f of negative x. Apply the negative. I get this. But I have originally f of x and I have f of minus x here and negative f of minus x right here. We're going to see which ones are equal. Are these equal or these are equal? Well, I have x cubed plus 2x and I have x cubed plus 2x. I think these are equal, which means the black one and the green one, looking at the colors, are equal. But that is f of x, and that is the opposite of f of negative x, meaning this is an odd function. Now, a vertical stretch and compressions. If the original function in blue is called f of x, multiplying outside by 2, it's going to stretch it by a factor of 2. Multiplying up front by 0.5, like half, you're going to shrink it, or called vertical compression or horizontal stretch. Either way, some books they call it horizontal stretch. If you want to stick to vertical, that's called vertical stretch, and this is called vertical compression. If I have x cubed graphed, we know that f of 2 equals 8, because 2 times 2 times 2 is 8. But it looks like this one here is having the same scale as this grid, but looks like something happened here. It's like somebody pushed it from the top and made it compressed. Well, if you zoom in and look at it, it looks like 2 is not going to 8, 2 is going to 2, as you could see. So one way to find the factor that you need to multiply up front, this is one way to do it. G of 2 equals 2, we know that. But G of 2 equals, it's supposed to be 8. If I multiply it by 1/4, I'll be at 2. And that will be my factor. That's one way to do it, and that's not the only way. I'll show you more in the coming slides. So from here to here, it's not exactly x cubed, it's 1/4 x cubed. Here's another graph. This is more practice of shifting. It looks like it's 1, 1. So it's the same like the original function, but shifted to the right 1 unit. And that's how we write it down. X minus 1 to the second. One more time, you could test it by plugging in 1. You get 0. 1 minus 1 is 0. Yes, at 1, I have the output 0. And as you can see, I'm marking these points to show you that there is no compression. There is no vertical stretch. So there is no number up front different than 1. Here's another example. If this is a square root, it looks like we took it to the left and we took it down. And it looks like there is no vertical stretch. Originally it goes from here to here, like 1, 1, then 4 takes you to 2, and so on. So that's a 3, 1, 2, 3, 4, 1, 2. That's like a square root of 4 equals 2. So it's like graphed differently or different place. But we know the square root of 4 is 2, so the scale is the same. There is no vertical stretch. That is exactly what I'm trying to show you. So it comes from the square root of x, but we're going to add 3 because we took it left 3. Subtract 1 outside because we took it down 1. Here's another graph. It looks like the angle is the same, like original absolute value, but we are taking it to the right 3 and down 2. And that should be the graph, and that should do it. The video after this video is about absolute value in more detail with a stretch and it's not going to be a lengthy video, so stick with me and you'll see it. And hopefully tonight I'm going to be recording more videos. This is my second video today, so I'll have the third one tonight. Actually, I have also another video after the absolute value, which is all about functions in detail, which is chapter 4. So today for algebra playlist, I'm uploading 4 videos. I'll see you on the coming video, and thank you for watching. Thank you for watching. Don't forget to hit the like button, subscribe to see some more, and I'll see you in the next one.